Good afternoon, everyone. Welcome, and thanks for joining us this afternoon for the Weather Ready Nation Flyers presentation about low-level turbulence and wind shear. Just a couple of housekeeping items before we get started. First of all, this presentation is going to be recorded, so it will be eventually available on our YouTube channel. And you will also be getting Wings credit for being here as well. So those should hopefully answer a couple of your questions right off the bat. My name is Chelsea Kenyon. I am from the Kansas City Center Weather Service Unit, and I'll be joined today by Sarah Teefee, who is with the Weather Forecast Office here in Topeka, Kansas, and also one of our local pilots extraordinaires, Mark Boguski, and he will be talking as well. So you'll hear from all three of us as we go. We also have a slew of people in the chat room ready to answer your questions, and we'll save a little time at the end for a Q&A. So let's go ahead and get started. I'm going to turn off my camera so you can see the important information on the screen. So we're going to start off here with low-level wind shear and low-altitude turbulence, and how to tell the difference. There's a lot of questions sometimes about this and how that is supposed to be handled. So we'll start with the statistical analysis, kind of lay the table for you here. Looking at the general aviation accidents over the last 10 years or so. This was actually recently released at Oshkosh this past year by the NTSB, if you were there. So it shows a gradual decreasing trend for the total number of accidents as well as the fatalities. And you can see we're definitely headed in the right direction, slowly but surely. So that is definitely good news. But as we break things out and look at the different causes of accidents, when we look at the weather, you can see adverse winds actually does account for a large number, the largest number of aircraft accidents in the system. But I want to point out that encounters into IMC, visibility, and also low ceilings, as well as darkness, cause the most fatalities. So they do have higher fatality rates. But adverse winds do cause the highest number of accidents for GA. And when you look a little deeper into those weather-related findings, you can see that wind by far outweighs all of the other causes of accidents, but the fatality rates are much, much higher for ceiling visibility and precipitation encounters, light conditions, and convective weather. So you can see wind causes a lot of problems, not as many fatalities, which is great news, but just want to put it in perspective for you so you can kind of see how things play out. When we look at weather-related accidents, 22% account for the total number of accidents. So the weather accounts for 22% of the total accidents. And you can see adverse winds actually account for more than half of the weather-related accidents in the system over about the last decade. Wind shear, I want to point out there on the top left-hand corner, is about 2%. So wind shear, as opposed to other types of adverse winds, does not cause as many accidents as adverse winds do. And then if we break it out even further into fatalities, you can see that weather accounts for almost 30% of the fatalities in the system, but low ceilings and visibility are by far the biggest killer. So wind shear, again, only counts for about 1%. So we're not talking about something that causes a lot of fatalities or even accidents with wind shear, but adverse winds does account for a large percentage of those accidents in general. So just laying the groundwork for you here. I'm going to hand it over to Sarah Teefee now, and she's going to start talking about wind shear.
Great, thank you, Chelsea. Good afternoon, everyone. Again, I'm Sarah Teefee. I am a meteorologist at the National Weather Service Forecast Office in Topeka, Kansas. I also work just very part-time over with Chelsea and her crew at the Center Weather Service Unit in Kansas City. But for the next about 8 or 9 slides, we're going to get into the meteorology of things here and talk a little bit more in depth about wind shear versus low-level wind shear and low-altitude turbulence, and some of the key features that you can use to distinguish between the two. So for starters here, what is wind shear? Many of you may be familiar with what this is, and really simply put, this is just a change in wind speed and or change in wind direction. And in this case, we're going to focus on vertical wind shear, which is that change about a vertical axis. So oftentimes in the atmosphere, you're going to see both things happening. As you go up, you're going to see the wind typically increase with height, at least for a little while. And that is because there's less friction aloft compared to at the surface. And then oftentimes, not always, but oftentimes you're also going to see that wind direction change a little bit with height. So usually we're going to see a little bit of both of those as you go up into the atmosphere, and that is what wind shear is. Let me see if I can control the, yeah, did I get it? Yep. Oh, wait, going too far. Sorry. Here we go. Okay, so there are two types of low-level wind shear that we're going to talk about, convective and non-convective. So when it comes to convective low-level wind shear, and as you all are probably well aware, there's many hazards that are associated with thunderstorms, which is why pilots should just in general avoid thunderstorms. But the wind field specifically within and surrounding thunderstorms can be quite complex. So your organized thunderstorms are going to have both updrafts and downdrafts. So they're going to have air rushing up into the storm, and that is an updraft, and also more dense air rushing down out of a thunderstorm, and that is the downdraft. As you can imagine, when we have a downdraft and it encounters the surface, that wind and that air is going to spread out in all different directions, and that is shear. So when that happens, you can experience sometimes rather intense and dangerous shear. An extreme example of this would be a microburst. Microbursts, unfortunately, can be difficult to forecast with a lot of lead time and can be difficult to warn with a lot of lead time, but they can be very hazardous to aircraft. So this is one reason why you want to avoid thunderstorms and some very intense shear that can be happening underneath that storm. As you know, there are many other convective hazards that come with thunderstorms. We're talking a little bit about turbulent conditions, low-level wind shear, those strong gusty surface winds that will often happen with those downdrafts out of those thunderstorms, or even out ahead of it with some gust fronts that you may see with thunderstorms, but also icing conditions within those cloud layers, lightning, then you're going to have the localized IFR conditions with your lower ceilings and poor visibility due to precipitation. So when we have thunderstorms in the forecast, we may not talk specifically in like a TAF about these other conditions because they are implied. So when you see thunderstorms in a TAF and in an aviation forecast, you can assume that all of these other hazards are going to be there with them. And if there are thunderstorms, you should see either convective SIGMETs that are issued by the AWC or some CWAs that are issued by the local CWSU offices. And then what we do at the WFO, like where I am in Topeka, we issue those TAF forecasts and we will have the TS mentioned in there, or vicinity, meaning that we'll have thunderstorms within 5 miles of an airport. One thing to note is that you don't need a thunderstorm that has the thunder and lightning to have turbulent conditions or to have some shear or to have unstable air. Even showers can have that, and areas around rain showers can have unstable and turbulent conditions. And virga, I've heard pilots talk about even some pretty turbulent conditions around virga. And what that is that's precipitation falling out of a cloud but evaporating in a drier layer in the atmosphere before it reaches the ground, and that can cause a lot of bumpiness. But again, thunderstorms characterized by the updrafts, the downdrafts, you've got the turbulent conditions, the icing, very complex environment, so certainly avoid that by all means. Now for non-convective low-level wind shear, your classic setup is when we have what's called a temperature inversion that has developed in the atmosphere. Generally speaking, during the daylight hours, we probably all know that usually the temperature will decrease with height into the atmosphere, and that's because we have solar radiation that heats the Earth's surface and the air just above it. So as you go up, the atmosphere cools down. Well, the opposite happens sometimes at night when the surface emits long wave radiation into the atmosphere. And so the surface is actually cooling faster than the air above it. And if you had a pretty warm day, you may have a layer of warm air that resides above the surface. And so now you have this inversion. You have your temperature actually increasing with height. And this often occurs on clear, calm nights. One way this may look, and this is from the schematic here is from a buff kit sounding, which is something we meteorologists will analyze quite a bit for a lot of different reasons throughout the day and the night, but this is what an inversion might look like on a forecast sounding. The red line that you see here is the temperature line, and as you can see, the temperature is increasing with height, just like what the schematic above is showing you. And then over there on the right side, there's a wind profile, and you can see that the winds are actually turning a little bit with height, a little bit of that directional shear we talked about, and also increasing with height. And so at the top of that inversion layer, you have what's called this discontinuity line. And oftentimes we see light or decoupled winds below the inversion. Those winds are decoupled from the winds aloft. And then you have your stronger winds at the top of that inversion layer or just above. And so this is what you're going to experience as low-level wind shear. Once you get to the top of that discontinuity level, or right there where that's happening, you're going to experience an abrupt increase in the wind, and that is low-level wind shear. One way that you can really tell a good difference between low-level wind shear and just more of a turbulent type of environment is that with low-level wind shear, you're going to experience a gain or a loss, but not both. If you experience both, then you're in more of a turbulent kind of environment. So that is low-level wind shear. Let's move into talking a little bit more then about low altitude turbulence. And again, with low altitude turbulence, we have shear. And this is shear that's usually in the form of eddies or waves. And it's typically smaller in scale and more unorganized than low level wind shear and can be a little sporadic. Over here on the right is another view of a buff kit profile of the wind. And in this case, we don't see as much directional shear. You see that the direction is fairly uniform as you go up out of the south-southwest, but you do see a gradual increase in the speed of the wind. And that's going to cause some rotation of the air and some of those eddies that can cause some turbulence when you're flying into and through those. Another phenomena that can cause some turbulent conditions is a low-level jet. What exactly is a low-level jet? Well, a jet stream is simply a fast-moving current or channel of air. Typically, it's pretty narrow in terms of its horizontal extent, and jets develop really for a variety of reasons, but primarily due to differential heating of the Earth's surface. We have a couple of images here from a model that are showing the winds at different heights in the lower part of the atmosphere. On the far left, this is 850 millibars, which in this area is usually about 4,000 feet up or so. And in that example there, we've got a jet stream of 50 to 60 knots that had developed at that time, a little bit lower than at 925 millibars. The wind's still pretty strong there. We would consider that a jet, not as strong as 850. And then at the surface, in this case, the winds are a little bit lighter, but this is where we have a little bit of a trough. And so out ahead of that trough, we see a strong stream of air that has developed. And oftentimes, if you experience turbulence with jet streams, you're going to experience that on the edges of the jet stream or as you're entering or exiting, because again, that's where you have a difference in the wind. So that's where you're experiencing a little bit of shear around the edges or as you enter in or exit the jet stream. Some other common causes of some low altitude turbulence includes mechanical mixing and daytime heating. I'm going to touch on both of those a little bit more in the next slide. Also, surface boundaries and fronts. That's where you have air masses of different density coming together. And so again, you see a difference there in the wind, and that can cause some of that turbulence. Oftentimes, if we have a jet moving over a hilly terrain or a mountain range, you're going to get gravity or mountain waves to develop downstream of that terrain. And then also strong surface winds can cause some of that low-level turbulence that you might experience. So a little bit more on mechanical turbulence and then the daytime heating. When it comes to mechanical turbulence, winds at the surface, like we hit on a little bit earlier, encounter a lot of friction and a lot of obstacles. We've got trees, we've got buildings, we've got different terrain features. So when the wind encounters those, it has to travel around those obstacles, and that creates eddies. And then those eddies can be carried downwind in the prevailing flow, and a pilot might experience that turbulent condition downstream of those obstacles as a result. And then when it comes to daytime heating or thermals, Again, we have during the day, we have the sun heating the surface of the earth, and that warms that layer right above the surface. And warm air, as you probably know, is less dense than cold air. And so you've heard the saying, warm air rises. And that is what we see in the case of thermals. We see some warm pockets of air due to the heating of the Earth's surface rising into the atmosphere. And we now have a kind of a mixing, the boundary layer is mixing together in this situation. And I've flown in airplanes many times when I've felt a little bit of that turbulence, and I'm thinking, oh, that's the thermals that are happening right now. And oftentimes when that's happening, you might see some cumulus clouds start to develop, just some fair weather cumulus clouds. And you'll probably have kind of a bumpy ride where you have the thermals and where you have the clouds. But if you can get above that cloud layer, it's going to be a lot smoother, because that mixing of the boundary layer only happens really to a certain height. And that height can vary just depending on the conditions that day. Tends to be a few thousand feet off the surface. Typically, it's higher in the warm season when we have more intense surface heating. But these things all can cause some of that turbulent conditions, again, that you might experience. And again, the main difference between low level wind shear and low altitude turbulence is the loss and the gain, and then also the fact that these types of things, the mechanical turbulence, the thermals, are going to be a little bit smaller in scale and a little less organized than low level wind shear. And I think with that, I send it back over to Chelsea for PIREPS.
All right. Thank you very much, Sarah. So that was the science behind turbulence and wind shear. Now I want to apply that to aviation and being a pilot. And so I work in the CWSU, which is the Center Weather Service Unit at Kansas City Center. So I deal every day with pilot reports and air traffic controllers. And so that's my perspective. So pilot reports are our bread and butter. This is what we use to verify our forecast, to tell the controllers what's going on. So pilot reports are very, very important to what we do. And one thing that we notice is that pilot reports for low-level wind shear are often mislabeled. And a lot of that is just because of the altitude where the pilot is experiencing those things. So here's a couple of examples of pilot reports. And again, PIREPS are subjective based on the type aircraft. And so obviously smaller aircraft are going to experience more turbulence in certain conditions than larger aircraft and so on. But when you're looking at low-level wind shear, what we see the most oftenly reported is this plus minus 10 knots landing or taking off on short final. You see those kinds of things. The plus and minus indicates to us that that's a speed change in multiple directions. That by definition is turbulence. Even if it occurs below 2,000 feet and you experience it as shear, if it's coming from multiple directions, it's actually turbulence. So we don't expect anybody to just suddenly change the way that they report, because you have a lot going on when you're below 2,000 feet if you're flying. So we understand that sometimes it's just easier to call it low-level wind shear and move on, because that's something easy that everybody knows how to report, but it's actually turbulence. So when we as forecasters look at that, we know that that's actually turbulence. If you look at that MKC report, that second one down, it's minus 15 knots on short final. That actually is low-level wind shear. So they experienced a single direction change, and that is low-level wind shear below 2,000 feet. The one at Oklahoma City there, you can see those, because they were over 10 knots, should have been reported as urgent PIREPS, but nonetheless, they were a single gain or loss, well, in this case, a gain of 15 knots or 25 knots, and so that is low-level wind shear. The Joplin report down here at the bottom, I wanted to point out it's a plus or minus on during descent to runway 18. And so that is turbulence, and I wanted to pull up the surface observations around that same time, and you can see the gusty winds in the observations there. So they were gusting from the southwest about 25 knots. Joplin, there's a little bit of terrain down there as well, so you have some mechanical turbulence going on. So that is gusty winds causing turbulence. It is not actually low-level wind shear. So just something to be aware of as you're reporting things. We don't expect wholesale changes going on with the way that things are reported, but it would be good to know the difference. So here's where the confusion usually happens. This was a particularly windy day across much of the Central Plains and the Midwest. And you can see the red box there is actually a low-level wind shear air met. And you can see there's a lot of reports there. Those little squiggly lines are actually low-level wind shear reports, but they were actually turbulence. So you can see on the right-hand side the list of pilot reports that we got that day. Most of them are plus minus 15, 20 knots or so. That's actually turbulence being reported as low-level wind shear. So there are a couple there that, well, there was two that were actually correctly reported. One at Chicago had the wind velocity plus or minus 20 knots. That is actually correct, right at 2,000 feet. And the Lafayette, Indiana one, low-level wind shear plus 20 knots. That one was correct as well. And that's getting up pretty close to where that air mat was starting. But everything, all those little squiggly lines south of that or west of that, you can see most of those reports ended up being actually plus minus reports. So this was a very windy day. We had widespread turbulence going on, but there was some low-level wind shear in there. So it is a much more localized phenomenon than it may seem when you see a great big low-level jet sitting across the plains. So, and I also want to just quickly mention that this is just the scenario we tend to see in the middle of the country. There are other things that do cause low-level wind shear in other parts of the country. So things like valley breezes, sea breezes, marine layers, all of those kind of things can cause low-level wind shear. So when you do see it in a TAF, pay attention to it, take a good hard look at the winds and evaluate the situation and know the risk that you can handle as a pilot.